Not really. Here we go. All right, last time we introduced quite a few terms and we ended up talking about grammars. I wanted to clarify a couple points that were clarified a little bit after class, just to be absolutely sure we're all on the same page with regards to this example. So we get this quadruple. The first element is the set of non-terminals. These are the variables, you might think of them as. We have our terminals. These are the actual characters that appear in a string. So when we can say this string appears in a language that's accepted by this grammar, that says that there is a way to derive it by replacing these non-terminals with these rules relating to terminals and non-terminals. And then this is an example derivation. So we start with just the single non-terminal s, and from there we must find a way to derive the string from there. So we just continuously replace a left-hand side with a right-hand side until we have a string of only characters in the alphabet. This tells us what the start non-terminal is, and this P is the list of productions that are right here. So the productions are just the rules. So this S, we apply this rule, and that replaces this S with the right-hand side ASB. So that becomes that. We take this S, we replace that with this ASB, carrying over the A, carrying over the B. And then we replace this S with nothing. Let's actually make that go into the correct place following the second rule that's right there. And at this point, there are no non-terminals left in the string. And that tells us we are done. And it also tells us that this string, AABB, is a string that's accepted. It's in the language of this grammar. Were there any questions or clarifications on that? It was the last thing we did at the end of class. I just wanted to review it, make sure we were all on the same page with regards to what this is doing, how you can use these rules, starting with the start non-terminal to derive a string. This tells us that there's a shorthand, a way to replace S via some number of productions, 0 or more productions, that get us to this string. That star means the same thing you did in the star closure, just that 0 or more.
So is it always going to be like, here we have the start string of S, which is like the non.
Yeah, it's the
like that?
Yeah.
Okay.
Yeah, we can decide that it's called something else, but in this class, I will always use S as that start variable, that start non-terminal that we will use to derive. But the rules of the grammars and the language that we're trying to represent will change. The alphabet will change. Yeah, that's the general idea of a grammar, is to find a way to represent the rules, the syntactical rules of a language. All right, we're going to dive into an exercise. Now that we have a little bit of experience with grammars, let's find one. So starting with that start non-terminal S arrow something, we want to find a grammar that generates A to the N, B to the N plus 1 for all N greater than or equal to 0. The hint I will give you as you start is start with the grammar from the last slide. It's very similar to that, because remember that generated A to the N, B to the N. So how would we add an extra B? Everything we do in this class does not have to be individual. Feel free to talk to a neighbor, a small group around you. Check your answers, talk through your logic, learn from each other, the good stuff.
Can you go back to the previous slide really quick?
Yeah.
That would be really funny. That should be really easy. Right now it's just a, one of them is just empty. And the second one is just
If you think you have an answer, how might you verify it? Come up with some strings that are in this language, a to the n, b to the n plus 1. What are some examples of that? Is the string b in a to the n, b to the n plus 1? Yes, that's n equals 0. ABB would be n equals 1. AABBB would be n equals 2. So these are all strings that are in this language. So once you have a grammar for this, you should be able to produce this via some sequence of productions for each one of these strings. There are other strings that are not in the language that you should not be able to produce with your grammar. There should be no way to follow the rules of the grammar to produce that string. So a string like A, AB, BA. None of those strings should be able to be produced. Who thinks they have an answer? Who wants some more time to work? You people, let's take a little bit more time. Anyone lost and could use some further direction?
I don't know, I kind of came up with a rule, but I don't know if it makes sense. Having A and then like a S, B, and then plus B.
Okay, that basically is a solution.
Okay.
There's It's slightly different syntactically than a plus, but I get exactly where you're coming from, and we're actually going to use an or.
Oh, okay, I see.
It's two different productions. But yeah, those are the two different productions. Just like on the prior slide, we had a first and a second with ASB and lambda. Replace that lambda with B. Does that work? Starting with the start non-terminal, how would we produce the first string in the table? S to B. So this one would be, I'm just going to make this reasonably long for the moment. We would say S arrow B. How would we produce the second string?
S arrow A, S, B, and then S arrow B.
So this S becomes ASB, this S becomes the B. And that produces the string that was at the beginning. How do we produce the third one? Let's see. There's one more repetition. So we're going to repeat this n times and then do this once. So in that order, this would give us S arrow ASB arrow ASB B arrow B. So this applies rule, well, if we call this rule 1 and rule 2, this applies rule 2, 1, 2, 1, 1, 2. Is there any way to make any of these strings with that grammar? The only way to start a string with a B is to immediately use production number 2, which terminates the whole thing immediately. There's no other string other than just B that starts with a B. Otherwise, we have to go through the first, and we recurse in the middle. So we've already made the very first character the first time we use this. Take this one as an example. We produce this A, that is this first A. We recurse to the middle immediately, and even though we made some more A's, they were the second A, and if we kept going, the third A, the fourth A, etc. We define that first character in the string with the very first selection of which production we take. So that immediately rules out anything else that starts with a B. And we see that via this first row, this first production, we are pairing an A with a B. There's no way to produce the more A's than B's or more B's than A's aside from one more B than A when we choose to make this. So we should not be able to make exactly the same number of A's as B's because we can't terminate on that first production. That forces us to recurse until we pick that second production. So we can't make this string, and we can't make an A by itself. There is no way to make an A without an associated B. So there's no way to make that. This is not comprehensive. This would just be, if I were writing this program, this would be my sequence of unit tests. And I have some evidence, this is not proof that this is correct, but I have some evidence that I have ways to produce the strings that I should be able to produce. And I have logic to say that I can't produce some of the strings that I shouldn't be able to produce. Any questions on that? Have everything we need from the board? Here's one solution. Here's another solution. There are multiple grammars that are exactly the same as the one that I wrote on the board, but are more complicated, and you can use multiple non-terminals to do so. Depending on how you visualize the problem, you may actually find that some of these make more intuitive sense to you or less intuitive sense to you. But there is not one correct grammar. There are often many correct grammars. This is why we all torture our grader this quarter. Our grader has to determine for every single one of your submissions, for every single problem, whether it's correct or not. Probably hasn't seen your exact solution before. This vertical bars signifies the logical exclusive OR, just meaning that we pick one or the other, but not both. So just like before, we wrote the two different productions, S arrow ASB and S arrow B. We could just make that a single, because it is really two productions, but you write it on a single line, S arrow ASB or B. So you can do that on a single line. That will save you some sanity eventually. We can specify that two grammars are equivalent if they generate the same language. And in fact, the grammar that I wrote on the board and these two other grammars all generate the same language. That A to the N, B to the N plus 1. Does the grammar have to be in a particular order? Not necessarily. The list of productions are a set. You have a set of productions, so the order of those productions doesn't matter. But I find that if you're writing homework or trying to communicate your answer to someone, order it in something that is easily determinable. Like the fact that I define S in terms of A before I write a production that defines A is very useful. If I wrote the A first and I didn't know how to derive the A and it wasn't the start non-terminal, then I would have to parse the entire grammar to figure out what your thought process is. So lay it out in an intuitive fashion if possible. Anything else before we move on to an introduction to automata? We will come back to grammars a bunch of different times in a bunch of different ways to represent a bunch of different kinds of languages throughout the course. But this is just kind of an intuitive introduction to what a grammar is. All right, an automaton is just a fun abstract model of a digital computer. We can write on paper a way for us to emulate what a computer does, which is transform inputs into outputs. So what do we expect an automaton to have? It needs some way to read input. The automata we are going to look at all read in strings. So there is some alphabet, all of the possible characters that could appear in a string. Then we are going to find some way to read that string. So we're going to read that string character by character from left to right. And at least for the first 2/3 of this class, we cannot go back. So we need a single pass from left to right on the string. And from there, we need to determine whether that string is in the language or not. So single pass, left to right. Once we reach the end of the string, we can detect that we are there at the end of the string. And from there, we can determine whether the string is in the language or not. It may need the ability to produce output. It's either going to accept or reject, or it's going to produce some kind of output in the form of another string. As it does that, it needs the ability to write to some kind of storage that potentially, some storage that it carries with it. So different automata have different types of storage. And we will start with one that has absolutely no storage. Finally, there's a control unit which is kind of its CPU. It determines which state it is in based on a number of states that you will define. And then there are transitions defined between those states that basically say, when I'm in a particular state and I am on a particular character in the input, then I should transition to this new state. So it looks very much like a transition graph. Way to visualize this, I see people are still taking a little bit of notes. If you're designing one of these, what you will design is the control unit. That's really the entirety of the design. You will be specified within you'll say produce this kind of automata that will limit you on what your input and output and storage is. Then you design the control unit. So you're going to tell me how many states there are, the transitions between those states, and a justification of why this design leads to every string that is in this language being accepted and every string that's not in this language being rejected. So some of these states in these control units will be final. If they are final and we end in that state, then we accept. If it's non-final and we end in that state, then we reject. So here's kind of a broad overview of what an automata looks like. The control unit is reading from the input file. It may or may not interact with some temporary storage. Think of this as your RAM. And then it produces some output. For the most part, this quarter, we will be talking about output that is just yes, no. But eventually, we will also talk about the ability to produce an output that is an actual string or a value. There are discrete time steps here. Think of them like CPU cycles. So at any particular discrete time interval, the automaton is in a particular state. We're looking at a particular character in the input. And so because of this, the next step is deterministic. We know exactly where we're going based on these two components, where we are and the character that we're reading. There is a single defined transition for where to go next, as long as our automaton is also deterministic. We will relax that constraint eventually. Don't worry about it for now. As we transition, we may be producing some output if we are outputting a string. The storage, the internal storage or the RAM of the system may change. There is a configuration, and the configuration is just a tuple of the current state of the control unit, what the input file looks like, including our position within that input file, and the values of the temporary storage, kind of a snapshot in time of what this system looks like. We will get a lot of experience with this. I know this is vague, and it will make a lot more sense as you start playing around with it. We can define the concept of a move as just the idea of moving from one configuration to another configuration via one of those transitions. So lots of different types of automata. We will talk about quite a few of them throughout the quarter and what they can do for us. For the moment, though, I'm only going to talk about a couple of them. The first is a deterministic automaton. If it's deterministic, then it's the equivalent of what we're going to call a total function. There is only one path, and there must be exactly one path that we can take for any particular configuration that we are in. Given that we are reading a particular symbol in the input and we're in a particular state in the control unit, there's only one place we can go. The much more complicated version to understand, at least initially, we won't start there, but we'll get there relatively soon, is a non-deterministic automaton, where there may be multiple possible transitions. So just like there can be deterministic and non-deterministic, there's a concept of an acceptor that just outputs a binary yes or no, accept or reject, and a transducer that produces actual string or numerical output. So this really is just an abstract model of a computer. Questions on any of these terms or ideas? This will make so much more sense once we dive into our first automata type, which we will do right after the next slide. So you might be asking yourself, well, we have computers. Why would we care about an abstract representation of a computer? Turns out that these concepts, formal languages that we talked about, grammars that we got an example of, automata, this abstract model of a digital computer, are used when we need to make syntax diagrams for programming languages, which is really the first theoretical step to creating a compiler. We need to understand how the syntax works. Imagine yourself writing a language. How do you know that it does everything that it needs to do syntactically? You might be writing some syntax diagrams, and that might require you to have an understanding of the underlying logical structure of your language. What is possible to write within your language? How would you do some things? Is there any ambiguity with regards to that? A lot of that information would be answered through the use of some syntax diagrams. Writing grammars for existing programming languages. Writing any compilers or interpreters for existing languages. So you might be used to, if you're programming in C using GCC, if you're programming in C++ using G++, if you're programming in Java using Java-C. But just because that existing compiler exists, that doesn't mean you couldn't write another compiler for it, a more efficient compiler. You could write an interpreter for a language that's typically compiled. You could write a compiler for a language that's typically interpreted. You can only really understand that if you can draw out the underlying theory behind the language and why it is complete, why it is efficient, why it does what that language is good at. So Java is very good at multi-platform development. C is very good at embedded systems and using something that's embedded because things won't change. And you need it to be bleeding edge efficient for the technology that it is on as that becomes out of date. So why you would use a particular language, and then from there, maybe some of the compilers that exist don't do everything that you want as efficiently as you want. So you could write a new compiler that optimizes it for your use. You can use it to reason about the correctness of a program. If you could represent a program yourself as an abstract representation, you could then use this to run your program because it is language agnostic. You can use it to convert one programming language into another. If you wanted to write a converter from Java to C++, etc. It's used in binary adders. I wanted to give you an example of a transducer here. I guess a couple of these are transducers. Converting one language into another is a transducer. Compiler is a transducer. But lots of potential applications. Any questions before we move on to our first automata type? All right, do it. All right, we ready? Are we caffeinated? Are we amped up? This is where it becomes real. Chug, chug, chug. All right. So I don't love introducing this first before really talking about them, but here is the book definition, the mathematical definition of a deterministic finite acceptor, the first automata type we are going to look at. So like the grammar was defined as a quadruple, this is a quintuple, 5 elements. It's much simpler than this makes it look. So we define this in terms of 5 elements. When PowerPoint crashes, it's probably using more RAM than this laptop has. PowerPoint likes to do that. My machine got too excited. So we have the set of internal states. This is your control unit. There are going to be some number of states that you specify. Each one of those states is a different position in the program, as you might think. We have the input alphabet. This is everything that could appear in an input string. Just the alphabet that we've seen before using exactly the same character. We have our transition function that is the cross product of the internal states and the input alphabet. This just tells us that for every internal state, we must have a transition defined for every possible input character that we might see. So if we're in state 0 and we read an A, what is the resulting state that we should be in? If we're in state 1 and we see a B, what is the resulting state that we should be in? For every state, there should be an outward transition for every single character in the input alphabet in order for it to be a total function, which is required in a DFA. One of our internal states is specified as the initial state. We're going to have a little arrow that is pointing at it that dictates this is where you begin, kind of like the start non-terminal is defined as this is what we begin with in a grammar. We need a state that is the initial state of a program, any program that's running on this automaton. Then we have a subset of the internal states that we dictate as final states. If we read the last character and we've transitioned to a state and we're kind of locked in that state as there's no more characters to read in the string, which state are we in? If it is a final state, that tells us to accept. If it is a non-final state, it tells us to reject. And final states are just determined or shown instead of having a circle for the state, as we will usually have in a transition graph representing a vertex, it'll be a circle with a circle inside it. And we'll see that here in a second with an example. So we assume initially we are in state, we're going to call this Q0 for the moment. So you can name your states whatever you want. I tend to just start with Q0 and increment them from there, Q1, Q2, Q3, unless there is something that state really represents. So kind of like naming your variables in a program, you can name your states something that says, I've seen an even number of this and an odd number of this. I've seen at least 2 of this. And you can find ways to name your states based on those ideas, makes your automaton a lot easier to read and understand. But if you are making something for an unknown language or the state that doesn't really have a ton of meaning in your design, I just go with the default of Q something. When we begin, the input mechanism, whatever is reading the string, it's going to be pointing at a particular character. It's going to point at the first character, signifying we have not read any of the characters in the input yet. For each move, as defined in move in the last couple of slides, we advance the input mechanism 1 position to look at the next character, and we transition from one state to the next state based on the transition of the character that we read. So this input mechanism will start consuming characters because we can't move backwards to the left. We are always moving 1 position to the right, 1 position to the right, 1 position to the right until we are done. Then we look at the transition function. We look at delta to try to determine where is it that we go. There's no determination. It tells us where to go based on the structure. As long as it is a total function, again, it needs to be in order to be a DFA. One example of how you might write this is to say, we transition from Q0 to Q1 on an A. This would be one way to write this. If you're not drawing this out as a transition graph, this just says we have Q0, that is the outgoing edge. Q1 is the incoming edge, and the edge label is an A. In English, if the DFA is in state Q0, reads an A from the input mechanism, it transitions to state Q1. And as I've already mentioned, we're actually going to visualize these with transition graphs. Vertices are your internal states. Edges are the transition labels given by our transition function. So let me actually show you one of these. A lot of description. It's time to visualize this. Here we go. So we have an arrow pointing into the initial state. This tells us Q0 is the initial state. Always include this arrow. It tells us where to begin, unlike with a grammar, with the S as this is the start non-terminal. If you name your states anything other than Q0, Q1, Q2, it's very ambiguous as to where to begin in this diagram. Even if you use something like this, always indicate the arrow that is the starting state. To show this is a total function, we can see that in Q0, there's an outgoing edge on a 0. There's an outgoing edge on a 1. The input alphabet is just binary. For Q1, there's an outgoing edge that's a 0. There's an outgoing edge that's a 1. For Q2, there's an outgoing edge that's a 0 and an outgoing edge that's a 1. There aren't more than that, and there aren't less than that. There's exactly one edge for every symbol in the input alphabet as an outgoing edge to every vertex in this graph. We see that Q1 is the final state. There could be multiple final states. In this, there's only one. But let's trace over this for some string. Someone give me some fun binary string. 4 or 5 characters, something like that.
101.
1101, great. So if we start in Q0, we start our input reading on the first character. And you can see between being in Q0 and having our input mechanism on a 1, it determines what that transition is. We take the outgoing edge that is a 1 from Q0, and we end up in Q1. We are now in Q1. The input mechanism has shifted from looking at the leftmost character to the second character. And given that we're in Q1, when we read this 1, there is only a single move that we can make. We transition from Q1 to Q2. That is the only outgoing edge that consumes that 1. So we move from Q1 to Q2, move the input to the next character. From Q2, we read a 0, we stay in Q2. There's a self edge from Q2 to itself. So we are still in Q2. Input mechanism moves one character to the right. We transition from Q2 back to Q1 on this 1. Input mechanism reads the end of string. So we now terminate and ask the question, is the state that we ended up in a final state or a non-final state? Since it was a final state, we would accept and say that the language that this deterministic finite automaton accepts this string. This is in the language defined by this state machine. Any questions on that? Hopefully that makes all the gibberish from the last couple of slides make a bit more sense. Yeah.
Do you have an example of one in this diagram that would put it not into a final state, so we would reject it?
Yeah. 1, 1. So Q0 into Q1, Q1 into Q2. We terminate. We're at the end of the string. Q2 is a non-final state. So we would reject. Worst X I've ever drawn. So you can see that this works for all strings of any finite length. I could throw this a string of length 100,000, and it would eventually, after 100,000 transitions, terminate and either accept or reject. So this machine works on an infinite number of inputs and perfectly segregates those that are accepted, that are in the language, and those that are not. Thoughts on this? Right. Things that we might be able to think about, given that we now have this idea. A DFA accepts one and only one language. Any thoughts as to why that is? Why doesn't it accept multiple different languages? It defines a particular language.
Because it's deterministic, as in it can always be predicted towards what.
Yeah. For each string, it ends in one and only one state. So because it's deterministic in that nature, you will always end up in a state, and that state will say yes or no to every single string, which means that for all infinite number of binary strings, the subset of those that are accepted is some language by definition. It can't be multiple languages because a string is either in the accept or the reject. For all binary strings, we can perfectly say this subset of them are accepted, this subset of them are rejected. Even if there's an infinite number in both the accept bin and the reject bin. But it is some decision about how to accept or reject. Is it possible to have two different DFAs that accept the same language? That's a fun question. The answer is yes. Why? Yeah.
Is it because you can change how many different states there are?
Yeah, you can create some ambiguity. Like I could go here, then back, then yeah, you can add extra states that don't do anything, that aren't particularly helpful, or that do what some other state was already doing. It's the same idea of you can write a program, two different programs that are exactly the same in terms of mapping inputs to outputs. If I wanted to print the numbers from 1 to 10, the program that just prints 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or accepts 10 as a guaranteed input and then goes through a loop that goes through from 1 to 10 and prints those out. Two different programs do exactly the same thing. Let's get some practice. Let's see if we can generate some EFAs that do some fun things. Write me a DFA that will accept any string that starts with the prefix AB and rejects any string that does not start with exactly that prefix. Again, feel free to work in groups.
Could you repeat the last part that rejects what?
Rejects anything that does not start with exactly that prefix AB. you're struggling to get started, talk to your neighbor.
Will our graph look the same because it's the same engine, we have two elements and then we also have. It has to be a full
A total function?
function, so they're gonna be the same.
You mean they would all be the same?
Because it's like the graph itself, not the states, not the stop states, but
Yeah.
the graph itself will be identical.
It doesn't have to be. There are multiple solutions to this. That said, there is one minimal solution to this.
I see.
Wait, so you're saying there's
No, this.
Q zero and Q one.
And then this B is.
You can only transition on a single character.
So if it's zero,
It's gonna be single character at a time.
Oh, see, okay, then I.
You're not consumed by single or multiple characters at a time. That is a good point.
Okay.
For the rest of the class, every edge must contain exactly one character. You cannot transition on a string.
It just goes on here, it's not.
If you've got a solution.
Good.
We've got something to tell.
So the thing is, if you're two, then this one.
Yeah, it is like you.
Yeah. But then you, but what if it's, if it's B, but then.
So that.
Yeah.
Oh. And then we.
A, B, over here. That doesn't show.
This one is also.
Oh,
I just.
So I see that.
Access. Well, there's only two defined. That's the standard. So that's gonna be.
Everything that does this.
It has to give the huge.
This class makes you a better pro.
And
Oh, going back to, yeah,
Because like it says.
yeah, there could be multiple incoming edges on the same symbol, but only a single outgoing edge of each symbol. But that's that.
Wait.
You just stop at.
See, like this one has a thing, you edge on itself. But you need these. Because it's a full. Total. That's.
I'm not sure where I just don't know.
No, the thing is, if it was just like this, it's fine. Right? It's A, B, and it stops. You can even do this, you can fine, but because it has a edge that goes here as well, that's what. This one's.
We are gonna be out of time. My challenge to you between today and tomorrow is to think about this and finish this off. We'll have an answer at the start of next class. I'm also gonna work to get a first assignment out to you at some point. Do note that this very first assignment will probably be a little on the longer side as I'm trying to shorten the rest of them, but I haven't gone through that work yet for this assignment. So as I give it to you, you will not have seen all of the material to do everything yet. But it would be due a week from today. That said, since it's a little larger in nature, I would recommend getting started on what you can do. There are going to be some basic grammar questions. Going over some of the grammar stuff that we've talked about. And since we haven't fully gone over anything DFA related yet, don't worry about that or anything later than that. But there should be at least a few problems you can get started with. If you don't hate yourself and want to procrastinate to the last minute.
Yeah, I don't know.
Office hours starting now if anyone has questions. Can you come check our? Yes.